In example 8.2, we're going to once again see the power of identifying both 2-force and 3-force members and how it can help us answer a question in a very quick kind of fashion. Here we have sort of a unique sort of structure where it's just a beam that sort of looks like it's suspended. It's got a cable over here that's a lot like a link, so it's really already automatically a 1-force situation or 1-force unknown. But we don't know the angle of inclination. That alpha is unknown. We do know that the self-weight of the beam has been represented as just a single concentrated force applied in the centroid of the beam, right in the smack dab L/2 location. But we have a roller over here to the left. And so because of that, then there's perhaps an intuitive kind of thing that you might already anticipate is going to happen in this problem. However, let's demonstrate through a 3-force member kind of idea exactly what has to happen. Okay, and so if we, I'm not even going to label this step. Well, yes, I will, because I've got to, right? The label, of course, is a free body diagram. That'll be the only thing we're going to have to do in this one, because look what happens when we draw this member and we put the forces on there. Note that that weight is purely vertical. And also note that the roller is on a horizontal plane, so its reaction has to also be purely vertical. And that kind of creates an interesting situation here that we've got a potential force couple at work, right? And notice that we've got this force out here, alpha, or force at B, that's at the angle, although unknown, of alpha. And there's one and only one way this thing can be in pseudo equilibrium. But notice 3-force member. That means that we have to have, out of those 3 forces, we have to develop a concurrent force system. The problem is look what happens here. That AY and W are purely vertical. They're parallel to each other. They'll never intersect. All 3 have to intersect in order for there to be equilibrium. So what's going to happen? Well, we know that there's got to be a vertical component at B, that if we were going to have equilibrium, we know that vertical component is going to have to be W/2 because it's halfway in there, and AY would have to be a W/2. But because the rope is initially at an angle, that would mean that there's a horizontal component to B. And there's nothing to equilibrate it because this is a roller support over here, not a fixed end, or excuse me, not a pin support, but a roller. So we have not static equilibrium, we have a dynamic situation, F equals ma. This thing is going to move to the right. It's going to accelerate to the right. And there's a lot of interesting things that begin to happen here. But after this thing shoots off to the right, it'll settle back and forth until at such point in time that B must be vertical. The static equilibrium position only pseudo exists if and only if alpha is equal to 90 degrees. That thing is vertical, right? Because of the consequence of what we have here, that we can't develop a concurrent force system, right? So let's show what that might begin to look like. And I say begin because you could quibble with what I'm about to show. You have to have something like that, right? That's sort of an equilibrium, but hey, whoa, wait a minute. If you really want to model what happens here, this cable, if it's a fixed length, right, when this thing moves to the right, B is going to drop down because that has to remain in tension. Right? We don't know what the length of that cable is. Let's call it L sub C for sake of argument. And so now the actual equilibrium position, after the thing kind of sways back and forth and you end up finally dissipating energy, then you're going to end up with something where the cable will have still be vertical. It's got to be that at L sub C. You have an incline length of L, which we don't know, and we've got, excuse me, the roller over here to the left. that would have to be your final actual position, but note that the free body diagram will still end up being the same. Go along the slope to L over 2, that's your centroid center of mass. We'll have W over 2 for the reaction, and internally we'll have W over 2 for our tension. That will be, and with respect to the beam, will be pulling up, or you could represent it as the reaction up here at W over 2. Right. And so that's an interesting little problem. That actually is not a stable structure. Right? We put any sideways force, it'll move again. But it has a pseudo or partially stable kind of situation as shown.